doing this. So if you've got a reactor that's been operating 10 years, we've got 250 years worth of fuel sitting right there on the reactor site to consume before we need any more fuel. Next. I think I've actually said all of these things, but I put this in here. This was from a Japanese magazine, and you see here's the little cold fusion reactor right there in the kitchen, helping it as she's cooking. In the meantime, in the U.S., we're stuck back in this technology. Next. Desalinization, we hear about a water shortage in California. And I will point out that California doesn't have a water shortage. We've got the world's largest body of water about 2 miles from here. What we have is a freshwater shortage, and we have the technology to convert that to drinking water. Desalinization, ion exchange membrane, reverse osmosis, and so on. Next. The problem is each one of these require energy, and there's significant cost not only for the production but also the delivery. In this particular information I found, from the Western Basin Municipal Water District, they were hoping to get 9% desalinization by 2020. I have no idea how they plan to do that. There has been a long battle to get a desalinization plant next to a conventional power plant in Carlsbad, just north of San Diego, for years by the environmentalists because of the fact that in the water that they put back into the ocean, it might have a slightly higher salinity content than the water that they pulled out of the ocean to do this desalinization. Next. Here's an application that we may not think of immediately, but that is for nuclear medicine. Use a lot of elements for both imaging and treatment. And currently all of these are about 2/3 of the world's supply of nuclear medicine that comes from Chalk River Reactor in Canada, and they use neutrons to irradiate materials and either fission or fusion generate these isotopes and elements. The reactor was shut down in 2007 for maintenance, and in less than a month it created a worldwide shortage of isotopes for nuclear medicine. And I'll point out a lot of these have half-lives in the order of 2 to 3 days. And what that means is you've got to produce this and then get it delivered around the world and for application in that length of time. Next view graph. And clearly a small reactor that provides neutrons could provide the ability to make these isotopes near the point of application. And you see some of these things you're down to a few hours. So if you have something that you need to inject into a person quickly after you make it, then this would provide the ability to do that. Okay, next. Okay, so back to the first slide. This was 1989. The physics community noted that the experiments aren't repeatable. Next. Currently, our experiments are very repeatable. There aren't any refereed papers. Next. We have many refereed papers, and others also have refereed papers. They haven't been replicated. Multiple experimental replications have been formed, and multiple results have been obtained, or consistent results have been obtained with experiments that were not identical. Next. It doesn't, if it's nuclear, where are the neutrons? Well, I think we have the best data showing that there in fact are neutrons, and it doesn't match theory. Next. Work to update theory is underway. I have a feeling that we have a much better chance of getting a theory to explain this from the people in this room than we have from the hot fusion. And finally, thousands of scientists worldwide attempted these experiments. Most failed. Next. Groups of scientists worldwide have successfully performed these experiments. And next. So back to the original question, how hot is cold fusion? Well, the answer is it's so hot, it's radioactive.
Yeah.
And next, it truly is the potential to become green nuclear energy. So thank you for your time.
We could do 4 or 5 questions. We're okay.
So why doesn't DOE give you money comparable to the one they spent on hot fusion? Because they haven't produced any useful commercial either.
I can't answer that. We have been in discussion with DOE. The Department of Energy a year ago set up this ARPA-E, which is the Advanced Research Project ARPA, Project Office Energy, and they had their 1-year anniversary in March, and they had a big show in Washington, and we actually participated. We submitted money, so we became a sponsor. That way we got a booth. Yeah. And we were by far the most visited booth. And when people would come up and ask what we're doing, we had talked about what do we tell them, and I said, well, if we kind of hem and haw around the bush, ultimately they'll say, well, this just sounds like cold fusion, and we will have lost any credibility we had. So when someone would come to me and say, what do you guys do? You know, and we had a booth and had a bunch of pictures and stuff there, and I would say, well, in the elevator speech, this is cold fusion 20 years later. Only where Pons and Fleischmann didn't have any papers, we have multiple papers. Where their experiments were repeatable, we have repeatable experiments. Where they didn't have any replication, we have replication. Where they didn't have any direct evidence of nuclear events, we have multiple diagnostics of nuclear events, including high energy neutrons. Would you like to learn more? And at that point, I had them rock back on their heels, and it's amazing how many people would stay around and talk to us and come back. Again, we got some feedback after the conference that we were the only new thing at the conference. Since that time, we've had meetings with senior people at the ARPA-E program office and DOE, but they are not inclined to fund us at this point. At least that's my interpretation. We're still talking with them.
Yes, in the hot fusion technology, there's a concept of break-even, that you have to achieve temperature, density, and time. Is there anything similar concept in cold fusion? Is there any threshold that is needed?
I'm sure there is. I'd really like to know what it is. The heat you talked about, and one of the things that we've talked about is right now we haven't done any experiments above boiling because the D2O goes away. There are experiments we could do there, for example, using some sort of eutectic salt. We could get up to higher temperatures. Those get much more difficult to do and more costly, and so we're not moving in that direction yet. Certainly, magnetic and electric field has an impact. Current density has an impact. Loading ratio has an impact. But most of the things I've just mentioned to you are more anecdotal and they're all nonlinear. So I can't hold one steady and vary another parameter, and then optimize sequentially like that because they're all a couple nonlinear oscillator, a couple nonlinear events. So I'm sure there is, and the reason I'm sure there is because anyone who's been doing this for any length of time, and we have had several cases where we've actually melted the palladium. Mm-hmm. And we go back and we look and try to figure out what were the parameters that caused that. And it's really difficult to come up with something that we can consistently say, yes, this is what caused it. Now what that does is that's like dangling this huge carrot out there because we know the energy's there. If we understand it and understand how to get it out, then we know it's there. But at this point, it's anecdotal and gut feeling from 21 years of working in this field.
Just wanted to say that what I found fascinating was the applications that I think really interesting here in terms of rather than trying to just the pure physics of it. But are you producing enough neutrons presently that you think you could actually, given funding, given backing, design a proof of principle experiment for generating enough neutrons to actually make it worthwhile to consider a fission project?
The short answer is no. We believe that our neutrons are being produced in bursts, just as the tritium was produced in bursts. We've seen evidence of that. Clearly, if we could produce a burst that would survive for continuously, then during that burst we are producing the flux that we would need, I believe, to have multiple commercial products. How far are we away from it? You sound like